Dear students, we'll continue looking at the cache optimizations which I have just mentioned at the end of previous lecture. So basically all the cache optimizations try to address and reduce the average memory access time. As you are already aware, there are three terms that will help us with the memory access time. One is the hit time, second is miss rate, and the third is miss penalty. Now all the cache optimizations try to bring it as close as possible to the to one cycle access or to the frequency of the processor. Now the first approach is to reduce the miss rate. Here we have few optimizations. One of them is to increase the block size. Second one is to increase the cache size. Third is to increase the associativity of the cache. For the second approach, we'll look at how to reduce miss penalty. There are two optimizations. One is multi-level caches. Second is prioritizing reads over writes. For the third approach, where we are looking at the hit time, we have one optimization which is looking at the address translation and removing it from the critical path. These are the 6 basic optimizations that we are going to see now. Apart from this, there are 11 other cache optimizations. For example, to reduce the miss rate, we can look at an interesting topic called prefetching. I'll quickly give a two statement explanation for this. We are bringing in a block only when it is accessed. Now, how about doing it a little proactively? By looking at the past accesses, if we are able to figure out where will the next block be, the address of the next block, and fetch it before the pipeline accesses it, it's called prefetching. Again, as you have rightly guessed, it is based on prediction. Based on looking at the stream of past accesses and trying to figure out where the next access would likely be. Now, such an approach can be implemented in the hardware or by help from the compiler itself. Another approach to reduce misses is to get the help of compiler, and there are a couple of optimizations at the compiler that can efficiently reuse the data. Now, few other approaches which are looking at the miss penalty are non-blocking caches, critical word first and early restart techniques, merging the write buffer, and something called pipelined cache access. If you remember the way the direct mapped or set associative or even the fully associative cache organization worked, we were extracting the index bit first and we send it to the row decoder which will select one set, and then we read out the tag and data arrays. After that, we do a tag match, and eventually, based on the output of the tag match, we select few bits of the selected block if it is a hit. Now, in this whole process, if we are able to divide them into independent steps, just like the way we did with the instruction execution, we have a pipelined version of the cache. It helps us to reduce the miss penalty. Also, it will help us to service many requests at a time. Now, looking at the hit rate, the other approaches are going for a simple and small caches, looking at something called way prediction. Again, it's prediction based. Fourth one is instruction cache. Trace caches specifically for instruction cache works brilliantly. and it has been implemented in most of the current x86 or Intel processors. The fifth one is banked caches. These 11 optimizations we will look at in the advanced architecture course. Now, caches were and are very interesting topics for performance improvement, and there are hundreds, if not thousands, of techniques that improve the cache performance. And recently, with the increased security concerns, people are exploring covert channel attacks, side channel attacks, so on and so forth at the cache level. In this course, we are just going to look at these 6 basic optimizations. To understand any of the cache optimization, it would help us to first categorize the cache miss into one of the 3 possibilities. The first category is the cache miss can be a compulsory or cold or first reference miss. As the name says, the very first reference to a block will always be a miss to the cache. So it's called a cold miss because the processor has never requested for that block. We haven't brought it to the cache from the memory. The second category of misses are called capacity misses. Because the cache is small, it cannot contain all the blocks that are needed by the program. So eventually the cache gets filled up and we would need to remove some of the block and get in the new blocks. These are called capacity misses. The third type of misses or third category of misses are called conflict or collision miss. Now, if we have a set associative or direct mapped cache, multiple blocks can be mapped to this single set. Now, because of the limited capacity of this set, only few of them can be present at any given moment. So, upon a miss, and if we find that the set is full, we need to remove one of them and fill in the new block. It would be a conflict miss if a block gets discarded or it was a victim block and evicted from the cache, but there was a reference for it sometime later. If there was no reference for it, then it would go to capacity miss. So in general, all the blocks which would have been hits in a fully associative cache but were missed in a n-way set associative cache are marked as conflict miss. This n-way can be replaced by 2-way, 4-way, 8-way or 16-way, so on and so forth. Now let's try to understand these 3 C's, more popularly called cold, conflict, and capacity misses. Any miss that would happen in an infinitely large cache is a cold miss. Because in an infinite cache, there will neither be any capacity or a conflict miss. In general, if there is an access to the block which has never been referenced till now, it would contribute to a cold miss. Coming to the capacity misses, all the misses which are not cold misses in a fully associative cache are capacity misses, because in a fully associative cache we will not have any conflict misses. The last category, which is conflict miss, is any miss that was previously in the cache but got evicted because of the conflict at the set. Now, to classify any particular miss into one of these 3 categories, a simple approach is there. To identify a cold miss at the cache controller, we need to keep track of all the cache accesses Basically, we are keeping track of all the addresses that have been looked up so far. Now, when a new miss occurs, if this address is not present in this list of addresses, then it's a new address, so it would belong to a cold miss. But if it is matching with any of the addresses which are already collected, it means that it's not a cold miss. So it can be either a capacity or a conflict miss. Now, once we have bifurcated whether it was a cold miss or not, if it is not a cold miss, now we need to distinguish it either as a capacity miss or a conflict miss. For this, we would need to keep additional entries for each set. Again, this would be part of our tag array, where we are storing the addresses of the recently evicted blocks. This can be called as misclassification table, MCT. Now, when a miss occurs, and if it is not a cold miss, then we would compare this address with the entries in the MCT. If there is a match, it means that it was earlier in the set, but it got kicked out because of the conflict. So it would be counted as a conflict miss. On the other hand, if there is no match, then we can say that it's a capacity miss. The confidence with which we can bifurcate a miss, or we can identify a miss either as capacity or conflict, would increase if we are able to maintain large number of entries in MCT. But it's not practical, so typically people go for 2 to 4 entries per set. Now, with that understanding, if you look at this graph, we have the cache size in the x-axis increasing from 1 kilobyte to 128 kilobyte, and on the y-axis we have the miss rate. If you look at one particular cache size, let's say 2 KB, as we increased from one way, which is basically the direct map, to two-way, to four-way, to eight-way, the miss rate is dropping. And specifically, what type of misses are dropping? It's the conflict misses. Now, if we increase the cache size, the miss rate again is dropping. Here, as the name says, the capacity misses are dropping, which is green color here. And no matter what the associativity is and what the capacity is, there are few misses which always remain. Here, the red bar, that would be our compulsory misses. Together, all the three would contribute to the total number of misses. Now, with this understanding, let's look at the cache optimizations. The first one is to increase the block size. A study has been conducted considering the spec 1992 benchmark suit, and what the designers have observed was, for different cache sizes 1K to 256K and different block size, which is 16 bytes, 32 bytes to 256 bytes, the miss rate was behaving a little non-linearly. What was observed was the number of cold misses were reducing, but beyond some point, the overall miss rate started increasing. For example, here beyond the block size of 64, when we move to 128, there is an increase in miss rate. The reason being, the number of unique blocks will reduce. So it will lead to either capacity misses or conflict misses. Also, there is an additional side effect, which is miss penalty. If we have a larger block, then transferring the block from the lower level to this level will take longer time. That will contribute to our miss penalty in the AMIT equation. So there is a trade-off that we need to make. So assuming that the main memory would need 80 cycles to access, and it will be able to send 16 bytes of data in 2 cycles, with the previous results, if we calculate the AMAT for various block sizes, this is the miss penalty based on the latencies which we considered. For different cache sizes, if we observe, as the block size increases, the AMAT was reducing till some point, which is marked as green here, and beyond that point the AMAT started increasing because the miss penalty and the overall number of misses started increasing. So we can increase the block size by looking at the AMAT, by doing a sweep and picking the point where it is the minimum. For example, here for a 16 KB cache, the optimal block size would be 64 bytes. Now there is a interesting example given in page C26. I would like all of you to go through that. It's looking at the same problem with numericals. Moving on to the second cache optimization, wherein we are increasing the cache size. Like you already know, with increase in cache size, the capacity misses will reduce. So I've simply reuse the previous graph. For if you look at one particular block size, let's say 256 bytes, as we increase the cache size from 1 kilobyte to 256 kilobytes, the miss rate dropped from somewhere, let's say 23% to 1 or 2%. There's a huge drop in miss rate because of increase in the cache. Basically, a bigger cache will help us to reduce the capacity misses. But accessing the bigger cache will take longer time, so the hit time can increase. Also, because it's a bigger circuit, we need larger area, and also activating such large circuit, row decoders, the tag and data arrays will take more power. So we need to trade off here again. The third optimization is increasing the associativity. I'm reusing the first figure we have looked at, where we had on the x-axis the cache size increased from 1 kilobyte to 128 kilobyte. The y-axis is the miss rate. For a given cache size, if we increase the associativity, the number of misses drop, the miss rate drops. So it's more or less straightforward that increasing the associativity will help us reduce the conflict misses for a given cache size and block size. But again, increasing the associativity can have an impact on the hit time because we need to compare multiple tags in parallel, and the output of these tags need to be used to select one word from the data mux. Now, if we are very close to the processor, it means that let's say we have a high associative cache in L1, because we are directly interacting with the pipeline, it can impact the processor cycle time too. So we can't keep increasing the associativity. Also, because we are trying to access multiple ways in parallel, the power consumption will increase. Here again, if you look at the AMAT values for different cache sizes for a particular block size, as we increase the associativity from direct map to two-way to four-way to eight-way, the AMAT increases drastically to some point. After that, it tapers off. So if you want to trade off our performance power, so this would be giving us an insight. For example, for a 4 KB 4 kilobyte cache, if we are if you want to consider two-way, then 1.67 would be the AMAT. Beyond that, if we increase the cache size, or beyond that, if we want to increase the associativity, then the benefit we are going to get is limited. So again, AMAT is giving us an insight on where to draw the line. There is another practice example in C28. Look at it. Again, we are the example deals with some numerical values, but the concept is how the performance of cache would change with increasing the associativity. The fourth optimization is multi-level caches. We already know that all the modern processes employ 2 or 3 levels of cache. It's because of this optimization. Now let's look at the AMAT equation quickly. If we consider only L1 cache followed by main memory, this would be our AMAT equation, where the miss penalty of L1 is the access time of the main memory. If you want to extend it with second level, AMAT equation gets expanded, and this would be the AMAT for level 2. If we have 3 levels of cache, again the second equation gets expanded to the third equation with the AMAT value of L3. Here the miss rate L1, L2 and L3 are local miss rates, where we are considering only the misses of that level. But in a multi-level hierarchy, if you want to get the overall miss rate, then we would need something called as global miss rate, which is basically product of all the individual miss rates. So this will give us a index of how well the overall 3 levels of cache are performing. Why would this work? Why would multi-level caches work? Basically, they will reduce the miss penalty, because instead of accessing the main memory after every L1 miss, if we introduce L2, we are going to incur the access latency of L2 every time it is a hit. So the number of times we are going to main memory gets reduced. Further, if we move from L1 L2 to L1 L2 L3, the access to main memory can reduce even further. So we can have a 3-level cache which performs much better than a 2-level cache. Also, multi-level caches offer some interesting trade-off. The first level cache can be small enough to meet the processor cycle time, both in terms of associativity and size. We can choose such that the hit time is not more than the processor cycle time. That is the stringent constraint. But if we have multi-level caches, the remaining levels of cache can be big enough, both in terms of capacity and associativity, so that the capacity and conflict misses can be reduced. So that is the reason we have multi-level caches almost everywhere now. Now here is a design question. We have 3 levels of cache. If the question is, can I add another level of cache, will it help me? So if we want to add a fourth level of cache and want to understand whether it would help us or not, we would need to expand the AMAT equation again. Only if the overall AMAT gets reduced, then L4 would help us. Couple of pointers. AMAT would reduce if the hit time of the fourth level of cache is much lower than the main memory. Pretty much straightforward. Another insight is the hit rate of this new L4 should be good enough that many more accesses would get reduced to the main memory. If the hit rate is low for the new level, then we would go to the main memory anyways. In that case, adding a fourth level will not benefit us. So there are a couple of practice examples in pages C31 and 33, very well described. I want you to go through. They are discussing about this particular design decision, whether we can go ahead adding a new level or not. The fifth optimization is prioritizing reads over writes. Like we have already known that reads have potential to stall the pipeline, but writes rarely do, mainly because of two reasons. One, Mostly the store instructions are consumers. Second, we also employ a write buffer. But when a write buffer is full, then the store instruction would need to wait till an entry in the write buffer gets freed. So that can create a stall in the pipeline. But the probability of writes causing the pipeline stall is much less than the reads. So again, we have our brilliant idea that we need to make the common case fast, which is reads here. So upon a miss, if there are multiple requests waiting at the cache level, both reads and writes, then we should prioritize reads and service them faster and send them back to the processor pipeline as soon as possible. This will reduce the overall miss penalty of all the cache levels after L1. Also, because the write buffer is present, upon receiving a read request, we also need to compare its address with all the entries in the write buffer, and if there is a match, it means that whatever data that we want is already in the write buffer, so we can discard the access to the cache and supply the data to the processor. It can improve our hit time too. There is a practice example in page C35. Go through it with some numericals. It will help you understand it better. Now the sixth optimization, avoiding address translation to be in critical path of the cache access. We are going to discuss it after the virtual memory lecture. In summary, we have looked at 6 cache optimizations. The first one is going for a larger block size. It can help us with the miss rate by reducing the cold misses, but it can increase the miss penalty. We can go for larger cache size. Again, it would help us with reducing the capacity misses, but accessing a larger cache can affect its hit time. The hardware complexity is slightly higher than the first optimization. We can go for higher associative caches. Just like larger caches, the miss rate will reduce, but the hit time can increase. The complexity again is similar to a larger cache. The fourth technique or optimization is multi-level caches. It will help us predominantly to reduce the miss penalty, overall miss penalty of in the AMAT equation, and the hardware complexity is much higher because we are introducing another level of cache in the hardware. It's quite costly. The fifth optimization is read overrides. Implementation is more or less straightforward and it will help us to reduce the miss penalty. The sixth one, implementation is again more or less straightforward and it will help us to reduce the hit time of the cache. With that, I'm going to conclude this lecture. Before that, the reading assignment is going through Appendix C3 of the Computer Architecture, a Quantitative Approach book, 4th edition by Patterson and Hennessy. Go through it. We can discuss if you have any doubts. Also, for the curious ones among you, if you remember, we have done under the hood assignment right at the beginning of the semester, where you looked at the hardware of your laptop or desktop and your mobile phone, and you have entered the details of the caches. Go through the cache details that you have entered. Now you can see whether you are able to figure out what all you have written at that point of time. It will help you to appreciate this cache module now. With that, I'll pause this lecture. Thank you.